Hello friends, today we will read about the distribution law from modern publication book. Now, introduction or definition of the distribution law. It is observed that when a solid or a liquid is added to a mixture of two immiscible liquids in both of which it is soluble. Example, iodine to a mixture of carbon disulfide and water, or succinic acid to a mixture of ether and water. It distributes itself between the two liquids in such a manner that the ratio of concentration of substance in two liquids is always constant at constant temperature. These observations were made by Berthollet and Jungfelix in 1872. However, it was pointed out by Nernst in 1891 that the ratio of the concentration is constant only when the solute has the same molecular weight, that is, the molecular state, in both the solvent. Hence, the generalization was put in a proper form by Nernst and is called Nernst distribution law. It states as follows: a solid or liquid distributes itself between the two immiscible solvents in such a way that the ratio of concentration of solute into solvent is constant at constant temperature, independent of the presence any other molecular species, provided that the solute has same molecular state in both the solvent. Thus, if a solute X distributes itself between the two immiscible solvents A and B, then if X remains in same molecular state in both the solvents, we will have concentration of X in solvent A upon concentration of X in solvent B is equal to C1 by C2 is equal to K. K क्या है? एक constant है ये. The constant is called distribution coefficient or partition coefficient. To test the validity of law, that is to verify law experimentally, different amount of solution of iodine may be added to mixture of water and carbon tetrachloride taken in different bottles. These are then shaken and allowed to stand. A known volume of each layer is pipetted out and then titrated against hyposolution to find out the concentration of iodine. Similar experiments may be performed with other solute and immiscible solvents. A few results of some earlier experiments are given in the tables on the next page. From these results given above, we observe that the ratio C1 by C2 is almost constant in each case within the experimental errors. Conditions under which distribution law is valid. The distribution law is valid only if the following conditions are satisfied. The temperature must remain constant throughout the experiment. The two liquids should be mutually immiscible. The amount of solute added should be small, that is, the solution should be dilute. This is essential because in certain cases the solute added affect the mutual solubility of the solvent. The solute must have the molecular state in both the solvent, that is, it should not undergo association or dissociation in any of the solvents or combination with any of the solvents. Thus, the law is not valid from the distribution of benzoic acid between water and benzene, because it has been observed that in benzene, benzoic acid undergoes associations to form dimers, that is, it exists as C6H5COOH2. Similarly, the law is also not valid from the distribution of any electrolyte like HCl acid between water and a non-polar solvent like benzene, CS2, CCl4, etc. because the electrolytes undergo dissociation in water. Now, thermodynamic derivation of distribution law. The thermodynamic derivation of distribution law is based upon the principle that if there are two phases in equilibrium, that are two immiscible solvents containing the same solute dissolved in them, the chemical potential of a substance present in them must be same in both the phases. From thermodynamics, we know that the chemical potential mu of a substance is a solution given by mu is equal to mu naught plus RT ln A. where mu naught is the standard chemical potential and A is the activity of the substance in the solution. Thus, for the solute in liquid A, we have mu A is equal to mu naught A plus RT antilog A. Similarly, from the solute in liquid B, we have mu B plus is equal to mu naught B plus RT antilog AB. But as already stated, since the liquid A and B are in equilibrium, mu A is equal to mu B. Therefore, mu naught A plus RT ln A is equal to mu naught B plus RT ln AB. The chemical potential is defined as the partial molar free energy, that is the change in free energy per mole, change of composition of component in the solution, keeping the composition of other components constant. The activity of a substance in the solution is its effective concentration. Further, at a given temperature, mu naught A and mu naught B are constant for given substance in particular solvents. Hence, at constant temperature, we have from equation 4 and ln A upon AB is equal to constant, and therefore A upon AB is equal to constant. This is exact expression for the distribution law. However, if the solutions are dilute, the activities are equal to concentration, so that the expression 6 is modified to Ca upon Cb is equal to constant, which is the original form of distribution law. Change in the molecular state and distribution law. As mentioned earlier, Nernst was the first person to point out that the distribution law in the form C1 by C2 is equal to constant is applicable only if the solute remains in the same molecular state in both the solvents, that is, it does not undergo association or dissociation in any of solvent or combination with any of the solvent. If, however, such changes take place in any of the solvents, then the law cannot be applied to the total concentration of solute in two phases, but only to the concentration of identical molecular species in two phases. In each of these cases, the distribution law equation is modified as discussed below for a few simple cases. When the solute undergo association in one of the solvent. Suppose the solute X remains in normal molecular state in the phase 1, but n molecules of its associate to form complex molecule Xn in phase 2, then the following two equilibrium will exist simultaneously. Now suppose the total concentration of solute X in phase 1 is equal to C1 and total concentration of solute X in phase 2 is equal to C2. Also suppose alpha is the degree of association of solute in phase 2, then concentration of associated molecules in phase 2, that is Xn is equal to 1 upon n C multiply C2 alpha, and concentration of unassociated normal molecules in phase 2 is equal to 1 minus alpha C2. Applying the distribution law to equilibrium, first we get concentration of solute X in phase 1 upon concentration of normal molecules of X in phase 2 is equal to constant, that is C1 upon 1 minus alpha C2 is equal to constant. Again, applying the law of chemical equilibrium to equilibrium, second we get concentration of associated molecules in phase 2 upon concentration of normal molecules in phase second is equal to constant 1 upon n C2 alpha upon 1 minus alpha C2 upon C2 alpha is equal to constant. Now that we will proceed this by completing it, the derivation. Now, thus in such cases when the solute undergoes association in one of the solvent, the constant value For the partition coefficient is obtained not for the ratio C1 by C2 but for the ratio C1 by n and root of C2. This relationship has been confirmed by studying the distribution of benzoic acid between water and benzene. The acid exists mainly as associated molecules in benzene solution. The following results were obtained. Grams of benzoic acid in 100 cc of water, 0.0150 gram of benzoic acid in 100 cc of benzene C2, 0.242, C1 by C2, 0.062, C1 by under root of C2, 0.0305. Thus, whereas the ratio C1 by C2 shows great variation, the ratio C1 by under root C2 is nearly constant. The formula C1 by n under root C2 is equal to k is commonly used for finding the value of n, that is the extent of complexity of the solute molecules in one of the solvent. This is done by finding out the concentrations C1 and C2 of solute in two solvent in a number of experiments. The value of n is then calculated as explained later. Case second, when the solute undergoes dissociation in one of the solvents as before, suppose the solute X dissolved in phase 1 without any change in molecular state but undergoes dissociation into Y, Z, etc. In the phase second, the following two equilibria will be set up. Open. Suppose total concentration of solute X in phase 1 is equal to C1 and total concentration of solute X in phase 2 is equal to C2. Also suppose the degree of dissociation of solute in the phase second is alpha, then concentration of undissociated molecules in phase second is equal to 1 minus alpha C2. Applying the distribution law to equilibrium, first we get C1 by 1 minus alpha C2 is equal to K constant called partition coefficient. Note, it is obvious that if the solute undergoes dissociation in phase 1 with degree of dissociation is equal to alpha but remains normal in phase second, then the formula obtained will C1 1 minus alpha upon C2 is equal to K. Similarly, if the solute undergoes dissociation in both the phases with degree dissociation alpha in each, then the formula will be C1 1 minus alpha upon C2 1 minus alpha is equal to K. From the above expression, the degree of dissociation alpha can be calculated. Hence, case third, when the solute undergoes combination with one of the solvent. Suppose the solute X remain in normal molecular state in phase 1, but the molecule of it combines with n molecules of the solvent as to form the compound molecules X ns in phase second. Then, as shown in figure 5.5, the following two equilibria will be established. Suppose concentration of solute X normal molecule in phase 1 C1, concentration of normal molecule in phase 2 C2, concentration of solvent molecules in phase 2 CS, and concentration of compound molecule in phase 2 CC. Applying the distribution law to equilibria, first we get C1 by C2 is equal to K, distribution coefficient. Again applying the law of chemical equilibrium to equilibria, second we get C upon C2 into Cs n is equal to K1 equilibrium constant. Since the solvent in phase 2 is present in excess in concentration, Cs remains almost constant in spite of combination with the solute X. Particularly if the solute is added in small quantity, that is the solution is dilute, thus Cs is constant, and so the equation 6 becomes Cc upon C2 is equal to K1 Cs n is equal to K2 another constant. Now at both the sides we get C2 plus Cc by C2 is equal to 1 plus K2. Now dividing equation 5 by equation 7 we get C1 by C2 plus C is equal to K upon 1 plus K2 is equal to K3 another constant. but C2 plus Cc is the total concentration of normal as well as solvated molecules of solute X in phase second. Thus, the above equation in fact implies that total concentration of the solute X in phase 1, total concentration of solute X in phase 2 is equal to constant. Hence, we conclude that when the solute enters into chemical combination with one of the solvents, there is no modification of distribution law equation except that the numerical value of partition constant is changed. Application of distribution law. The distribution law has been applied to study of problem of both theoretical and practical interest, a few of which are briefly discussed below. In, can- in calculating the solubility of a solute in a solvent, when two immiscible solvents are in contact with each other and solute is added in such a large excess that is saturated solutions are formed, then the concentration of solutions at this stage will be equal to their solubilities, assuming that the distribution law is applicable. For such concentrations, we will have C1 by C2 is equal to S1 by S2 is equal to K, where concentration C1 is equal to S1 is the solubility of solute in solvent 1, and concentration C2 is equal to S2 is the solubility of solvent in solvent 2. Thus, knowing the distribution coefficient K and solubility of solute in one of the solvent that in another can be calculated. In the process of extraction, the process of extraction is of great importance both in laboratory and industry. In the laboratory, the process is often used for the removal of dissolved substance from an aqueous solution with the help of organic solvents like ether, chloroform, carbon tetrachloride, or benzene. In the industry, the process is used to remove the impurities from the product. Basically, the process involves shaking of aqueous solution of substance with an organic solvent which is immiscible with water but in which the substance to be extracted is soluble. After shaking, the mixture is allowed to stand. Most of the substance passes into the organic layer from which the former can be separated out by distillation of the organic solvent. However, in order that the process of extraction may be more effective and efficient, the following two conditions must be fulfilled. First, the value of distribution coefficient of substance between water and extracting solvent should be greater in favor of extracting solvent. It is sometimes possible to increase the distribution coefficient artificially by making the substance less soluble in the aqueous phase. This can be done by adding some substance which depresses the electrolytic dissociation of compound being extracted. Thus, suppose that an organic acid which ionizes to a certain extent in aqueous solution is to be extracted with ether. If strong inorganic acid is added to the solution, the hydrogen ion concentration is increased and the ionization of organic acid is reduced because of common ion effect. In the solution, there will be greater amount of undissociated acid and hence the amount of extracted will be greater. Similarly, an organic base can be best extracted in the presence of a strong inorganic base. The addition of salts also usually lower the solubility of an organic compound in water and thus increases the distribution coefficient. Second, the whole of the extracting solvent available should not be used in one lot but it should be used in maximum number of installments. Suppose X gram of substance are present in 1 liter of aqueous solution. Also, suppose 1 liter of ether is available as extracting solvent and that the distribution coefficient of the substance between ether and water is 2. Now, if whole of the ether is used in one lot and X gram will be the amount of substance extracted into ether, then we will have concentration in ether upon concentration in H2 is equal to X upon 100 upon x minus x upon 100 is equal to 2. X is equal to 2 by 3x is equal to 0.67x. Thus, only 67% of total amount will be extracted in this case. Again, suppose the whole ether is used in two installments each of 500 cc. After shaking with first installment of 500 cc, suppose x1 gram of substance passes into ether layer, then clearly x1 upon 500 upon x minus x1 upon 100 is equal to 2. X1 is equal to half x is equal to 0.5x. Thus 50% of total amount is extracted out in operation. Therefore the amount of substance left unextracted is equal to x minus half x is equal to half x. Now 1 liter of aqueous solution containing half x gram of substance is shaken with the remaining 500 cc of ether. Suppose the amount extracted into ether by operation is x2 gram, then x2 upon 500 upon x by 2 minus x2 upon 1000 is equal to 2. X2 is equal to 1 by 4th x is equal to 0.25x. That is 25% of total substance passes into ether layer in this operation. Therefore total amount of the substance extracted is 50 plus 25 is equal to 75%. Thus, when 1 liter of ether is used in two equal installments, the percentage extraction increases from 66.7 to 75. Similarly, it can be seen that 1 liter of ether is used in 4 equals installment, the extraction increases further to 93.75%. A general formula can derived which gives the amount of substance when unextracted after a definite number of operations. Suppose W gram of substance is present in VmL of solution made in solvent A. Also suppose that V volume VmL of extracting solvent B is each time, and K is the distribution coefficient of substance between the solvent A and B. Now if W1 gram be the amount of substance left unextracted in solvent A after the first operation, then concentration in A upon concentration in B is equal to K. Now solving this equation, we get the amount of substance left unextracted will Wn is equal to Kv upon V plus Kv. In order that the extraction may be most efficient, clearly Wn should be smallest possible. This can be so only if the factor Kv upon V plus Kv bracket n is as small as possible. Now in this factor the denominator V plus Kv is greater than the numerator Kv, therefore Kv upon V plus Kv is less than 1, hence the above factor will be smallest possible when n is the greatest possible. So it follows that multi-step extraction is more economical than the single step extraction. Further, from the above equation it may be seen that Wn can never be equal to 0. However, large n may, in other words, extraction can never be complete. However, large number of extraction may carried out. Otherwise also it is clear that every time the substance left distribute itself between the two solvents, some quantity, however small, must be left unextracted. Note: for the purpose of numerical problem, it must be remembered that K is the distribution coefficient of substance between the solvent A already present and extracting solvent B. If K is given for distribution of substance between solvent B and A, the reciprocal of this value should be used in above equation. The principle of multi-step extraction holds good for washing and precipitate, whereby the impurities distribute between the liquid and the precipitate. Further, in Parkes process for desilverization of lead, also use is made of the principle of extraction. Silver is more soluble in zinc than in lead. Zinc is immiscible with molten lead. Thus, when zinc is added to argentiferous lead, a large quantity of silver goes into molten zinc layer, leaving the little silver in the molten lead layer. Thus, because the distribution coefficient of silver between zinc and lead is 300 at 880 degrees Celsius, zinc containing silver form the upper layer. Thus, by repeating the process, almost total quantity of silver can extracted from arseniferous slate. Now, in the distribution of degree of hydrolysis, let us first study some terms and expression related to salt hydrolysis. Hydrolysis constant. The general equation for hydrolysis of a salt Ba may be written as Ba plus H2O equilibrium Ha plus BOH. Applying the law of chemical equilibrium, we get Ha bracket close bracket BOH bracket close upon bracket VA bracket close bracket H2O bracket close is equal to K, the equilibrium constant. Since water is present in very large excess in the aqueous solution, its concentration H2O may be regarded as constant, so that we have bracket HA bracket close bracket BOH bracket close upon BA bracket close is equal to K bracket H2O bracket close is equal to KH, where KH is called hydrolysis constant. Since HA and BOH represent the molar concentration of free acid and the free base produced, and Ba represent the molar concentration of unhydrolyzed salt, the above expression for hydrolysis is constant may written in a more general way: KH is equal to free acid free base upon unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt is defined as the fraction or percentage of total salt which is hydrolyzed. For example, if in a solution of aniline hydrochloride 90% of salt is hydrolyzed into aniline and hydrochloric acid, the degree of hydrolysis is 0.90 or may be expressed as percentage with 90%. It is usually represented by the symbol H. H is equal to number of moles of salt hydrolyzed, total number of moles the salt taken. Expression for the degree of hydrolysis for solution of different type of salt, as salt of strong acid and bases do not undergo hydrolysis. Therefore, to talk of KH or H of such salt is meaningless. The cases of other three type of salts are discussed below. Salts of weak acid and base, strong base. Representing salt by Ba as usual, the hydrolysis may be represented as follows: Ba plus H2O equilibrium BOH plus HA, B positive plus A negative plus H2O equilibrium B positive plus OH negative plus HA. That is, in it is a case of anion hydrolysis. Suppose the original concentration of salt in solution is C-mole liter, the degree of hydrolysis at concentration. Then we have A negative plus H2 equilibrium OH negative plus HA. Original concentration at equilibrium C00. Hydrolysis constant KH will therefore is given by KH is equal to OH negative HA upon A negative. CH dot CH upon C1 minus H is equal to CH square minus 1 minus H. If H is very small as compared to 1, we can take 1 minus H approx 1, so that the above expression becomes CH square approx KH. H square approximately KH upon C. H approximately under root of KH upon C. H is inversely proportional to under root of 1 upon C. Thus, the degree of hydrolysis of a salt of weak acid and strong base is inversely proportional to the square root of molar concentration. Determination of degree of hydrolysis by application of distribution law. Suppose it is required to determine the degree of hydrolysis of aniline hydrochloride, which is a salt of weak base, aniline, and a strong acid. This method consists of two steps as follows. First, determination of hydrolysis constant. Aniline hydrochloride is hydrolyzed. The hydrolysis constant will therefore be given: KH is equal to free aniline, free HCl acid, unhydrolyzed salt. Thus, To get the value of KH, the aim is to find out the molar concentration of free aniline, free HCl acid, and the unhydrolyzed salt in an aqueous solution of aniline hydrochloride. This is done by shaking aqueous solution of aniline hydrochloride of known concentration with benzene. As a result of free aniline distributes itself between the two solvents, that is water and benzene, whereas HCl acid and the unhydrolyzed salt remain in an aqueous layer only, as shown. For a calculation of concentration of free aniline in aqueous layer. For this purpose, the concentration of aniline present in benzene layer is found by taking a known volume of this layer, evaporating of the benzene, and finding weight of aniline left. Having known the concentration of aniline in the benzene layer, that in the aqueous layer can be calculated if the distribution coefficient of aniline between water and benzene is known, which can be found by a separate experiment. Calculation of concentration of free HCl produced. From the hydrolysis equation, the number of moles of HCl produced equal to total number of moles of aniline produced. But total amount of aniline produced is equal to amount of aniline present in benzene layer plus amount of aniline present in aqueous layer. Each of these amount has already been calculated in step A above. Hence the total number of moles of aniline produced, and hence the free HCl produced, can be calculated. Knowing the volume of aqueous layer, the concentration of free HCl in aqueous layer can be calculated. See calculation of concentration of unhydrolyzed salt. From the hydrolysis equation, it is clear that the number of moles of salt hydrolyzed is equal to total number of moles of aniline produced or free HCl produced, which has already been calculated in step B above. Hence, knowing the initial number of moles of salt taken, the number of moles of salt left unhydrolyzed can be calculated. Further, knowing the volume of aqueous layer, the concentration of unhydrolyzed salt can be calculated. Alternatively, the aniline present in benzene layer may be determined by passing HCl gas through it, so that aniline is precipitated as aniline hydrochloride. Second, calculation of degree of hydrolysis. Knowing the hydrolysis constant Kh, the degree of hydrolysis of a solution of aniline hydrochloride having concentration C moles liter can be calculated from the expression H is equal to under root Kh upon C. Summary. Now we will read about summary. Nernst distribution law. A solute distributes itself between two immiscible solvents in such a way that the ratio of concentration of the solute in the two solvents is constant at constant temperature, independent of the presence of any other molecular species, provided that the solute has same molecular state in both the solvent. Mathematically, C1 by C2 is equal to K, called distribution or partition coefficient. Condition under which distribution law holds good: temperature should remain constant. Second, the two liquids should be immiscible. Third, amount of solute added should be small. Fourth, the solute should not undergo dissociation or association in any of the solvents or combination with any of the solvents. Third point, thermodynamic derivation of distribution law. The chemical potential of solute in two liquid A and B is given by mu A is equal to mu naught A plus RT and log A, and mu B is equal to mu naught B plus RT and ln AB. At equilibrium, mu A is equal to mu B, hence mu naught A plus RT ln A is equal to mu naught B plus RT ln AB. Fourth, change in the molecular state and distribution law. First, when the solute undergoes association in one of the solvents, example suppose in solvent 1, the solute remain in normal molecular state, but in solvent 2 we have an the formula is modified to form C1 upon under root of C2 is equal to constant. If the solute form dimers n is equal to 2, hence C1 upon under root C2 constant. Point 5, application of distribution law in calculating the solubility of a solute in solvent. If sufficient solute is added to the solution or saturated, we have C1 by C2 is equal to S1 by S2 is equal to K. Knowing the partition coefficient K and solubility in one of the solvent that is in the other can be calculated in studying the extent of association or dissociation of solute in the solvent. For association, C1 upon N under root C2 is equal to K. By heat and trial method, put n is equal to 2 and check whether k comes out to be constant. If not, try n is equal to 3 and so on. B. Logarithm method. Using the data of two experiments, the above expression is modified to form n is equal to log c2 minus log c2 dash log c1 minus log c1 dash. Hence n can be calculated. For dissociation, C1 upon C2 1 minus alpha is equal to K. Hence alpha can be calculated in studying chemical equilibria forming complex ion. In the fourth, in the process of extraction, we also use it. For the extraction of a compound present in solvent a solvent is added which is immiscible with solvent A, and distribution coefficient of the given compound is more in favor of extracting solvent. Fifth, in the determination of degree of hydrolysis. Thank you.